Hello everyone. In today's lecture, we'll be discussing how we can do the stability analysis of the system without solving. Here we're going to study the Lyapunov method, and based on which we can comment whether the system is stable or not. And also we'll cover Lyapunov first method, where we can study the system stability also by solving the full dynamics of the system. Before we proceed to the Lyapunov first method, we'll come up the motivational example, how we can do the analysis for the nonlinear system. So let's have an example. Here we're going to consider a very simple system, the mass spring damper system. The mass attached to a wall via the spring. This is the spring, and this is damper. And the position of the mass, let's define x from the equilibrium point. The simple equation, force balance equation for the system, we can write F, and this displacement x is there because of the force being applied on mass. So the force balance equation we can write F equal to mx double dot plus bx dot plus kx, and where where you can assume the a is the acceleration, which is nothing but dou square x dot t square, and x is the displacement of the mass, and x dot is the velocity, which is nothing but dx dt. And here we're gonna, since we are going to study the system, and what you have done in the previous lectures, that we are for studying the nonlinear system, we convert the system into autonomous form. For the autonomous system, as you have done before, the force assumed to be zero. So if the system is autonomous, if equal to zero, and for this condition, let us define this, the equation number one. The equation one yields to be mx double dot plus bx dot plus kx equal to zero. And here, let us assume the mass of this, the mass. So let's assume the mass m equal to 1 for m equal to 1. Equation 2 yields to be x double dot plus bx dot plus kx equal to 0. Now, if you notice, the system is basically second order system. The system is second order system. And here we'll convert the system into first order ODE. So for that, we have to apply the change of variable. So here, let us define, or you can write the system in state space form. We can write x1 dot equal to x2, and x2 dot equal to, we can write minus bx1 and minus k minus bx2 and kx1. So the change of variable basically you have used x1 equal to x and x dot equal to x1 dot, which is x2. So using this variable, we have come up the system into first order ODE. Now, since in Lyapunov this method, we will be using some energy function and through which we can check the system stability. It is different from the earlier lecture where we have used the phase portrait method. So here, let us define the total energy of the system at any time. So the energy, we can write the total potential and kinetic energy, you can write the total energy content in the system. It's defined by V x1 x2. So V is the total energy in the system. Now we are defining by V, and we can write half mv square plus the potential energy, you can write half k x square. Since we are assuming V to be 1, we can write, sorry, m to be 1, we can write half v square plus half k x square, we can write. Now we'll see how the time derivative of this v is going to behave. We'll have a lot of stuff in later lecture why we need to consider v dot to be decreasing function or increasing. All this stuff we'll discuss in more detail and how they are connected to stability. So here basically we have to check how the system total energy going to behave. So here we'll take the, here we can write this is the condition we have to follow. The V x, I can write V x is greater than 0. So here x actually can write x1, x2 vector. So, or we can write like this. V x1, x2 we can write. It is greater than 0 for x1, x2 not equal to 0. So this the condition should be valid for this energy function, and V x1, x2 is equal to 0 for x1, x2 equal to 0. So if this condition satisfy, and we can say this is the energy function for this particular system, we'll have detail in the later lecture how this condition being, we can write here. So now we'll see how the total energy of the system going to behave. Now let's see if the energy of the system is increasing or decreasing with time. So rate of energy which is the equation 4, or we can define this equation number 5, and this is equation 4. And rate of energy of equation 5, we can write dv dt, we can write dou p dou t dx1 dt plus dou v. Sorry, this should be x1 and dou x2 dx2 and dt. So here actually, so now we can find this function from equation 4 we can write. So here we can write dou v dou x1, we have kx1, and dou v dou x2, we are having x2. Now substituting these values in this equation, we can write dou v dou x1, we can write kx1, and dou x1 dt, we can write x2. This is already have defined here. This is defined here. So, and plus we can write dou v dou x2, we can write x2, and x2 dot we have by this expression. X2 dot this expression we can write here. So we can write minus b x2 minus kx1. Okay. Now if we solve this expression, we'll have minus b x2 square. So now if you notice here, this is basically, this part is always positive, this part is always positive, and this is negative. The whole term is negative. So it means dou v dt actually decreasing over time. And we can write here, and it is decreasing when its system goes to the equilibrium condition. And at equilibrium, the total energy of the system will be 0. So we can write here the energy of the system keeps on decreasing until the equilibrium condition equal to 0. So here, why it is equilibrium condition is 0? Because from this equation, we can write the equilibrium condition. We can write from this expression, equilibrium condition x1 dot equal to 0, from this x2 equal to 0, and from the second equation x2 dot equal to 0, and from this, since x2 equal to 0, x1 equal to 0. The equilibrium condition, equilibrium point, we can write, this is xc, or we can write x1, x2, this is actually 0, 0. So at equilibrium point, the function, sorry, the energy of the system is 0. We can write dv dt equal to 0 at equilibrium point, and for this be equal to some constant and very small in magnitude. So this is how we can comment the system, the autonomous system is stable. And why it is autonomous we are considering, because Lyapunov function, this theorem are valid for autonomous system. We'll have more details in this context later. So this is how we can check the stability of the system without solving the dynamics or equation. And this is very, very powerful tool to analyze the system. It should be noted that the total energy of the system, sometimes it is difficult to find. So, but we'll have some generalized rule how we can find the total energy of the system later in this context. And now we'll move to the. So I hope this part is clear. The first part, how we can check the stability of the system without solving the whole equation of motion. Later we'll have more example how we can do the same stability analysis for any other dynamical system. And this is just for motivational example. Now we'll move to the second part in this lecture, Lyapunov first method to study the nonlinear system. Here we will go through some basic. Already you have done this part before. How can linear the system? So here let's assume we have a nonlinear system. Let us consider. Let us consider a time invariant nonlinear system x dot equal to f of xu. And here we are assuming where f xu is continuously differentiable at its component of x and u. So here we are assuming x is the state and u is the control or any other perturbation in the system. So here we can assume this is the nonlinear system. And now we're gonna see how we're gonna look how we're gonna find linear model of the nonlinear system. This part already you have done multiple times in our previous lectures, but again we'll do this part because it is very important to study the Lyapunov first method. Here, let's assume the equilibrium point of the system. Let us consider the equilibrium point. Equilibrium point be defined xc and ue. This the equilibrium point is found to be for the system. And at equilibrium point, the function will satisfy. We can write at equilibrium point at xc ue, we can write f xc ue equal to 0. And here actually you can write the control u can be some 0 or constant, some value 0 or k we can write. So here 0 or constant, some constant value we are applying if there is control, or it is unless it is 0. It is unforced system. In the presence of perturbation, let's assume in the presence of perturbation, the system will deviate from the equilibrium point, as we have learned in our previous lectures, that we can write x of t, we can write xc plus dou xt, delta xt you can write. And similarly, we can write for the u part, u of t you can write u naught plus delta ut. So here we can write ue also fine, that is some equilibrium point, some value of the u. So here, dou xt and dou ut actually perturbations in x of t and u of t. Now we'll take the time derivative of equation. This is, let us define this, the equation number 1. This is equation 2. And if you take the time derivative of equation 1, taking time derivative of equation 1, we can write x dot equal to xc dot plus dou x dot. So it is function of time we can write. And since the equilibrium point assumed to be constant parameter, or sorry, constant value, we can write x dot of t, we can write dou dt dou sub t. This is actually, now if you substitute this expression in our nonlinear system here, x dot equal to f of xc, we can write x dot of t equal to, we can write xc dot t uh, plus dou dot t f of xc plus delta x and u naught plus delta u of t. And here, if you notice this function, this function will apply here, the Taylor series expansion. So using Taylor series, expansion, we can write x dot of t. This is nothing but x. Actually, here this part is assumed to be 0. So we can write x dot t. We can write f of xc u naught plus dou f dou x. F actually here function of xc ue, and delta x the partition in x, and dou f xc ue divided by dou u delta u, and we have the second order terms of dou square f xc ue divided by dou x square and delta x square plus dou square f xc ue divided by dou u square and delta u square. So this is we'll be moving to the higher order terms. So rest of terms we are not writing. So we can write this is higher order terms, which we can denote as xc ue u naught delta x and delta u. This you can write. So now what we'll do now, if delta x is very small, if you assume this delta x are very small, so this whole terms we can ignore in the equation, because these terms are assumed to be very small perturbations from the equilibrium point, because here actually we are studying the local stability of the system. So we can ignore this higher order terms. So we can write this expression, we can write if xc u naught plus dou x if xc u naught del x plus, or we can write one thing here also. Instead of this, we can maybe remove these terms, and the rest of the terms, the higher order terms, we can have many other terms. So these terms we can represent, these whole terms we can represent as h xc u naught dou x delta x and delta u. This we can write. So from the second order terms onwards, we can denote as the higher order terms. So here we can write dou f, dou x actually the Jacobian matrix for the state. So we can write this expression dou f1 dou x1 dou f1 dou x2 dot dou fn dou xn. So if you consider the system is nth order system, if you consider this system is a vector system and nth order system, so in that case we'll have the dimension of the matrix will be n cross n, and similarly the second row we can write dou f2 dou x1 dou f2 dou x2 dot dou fn, and sorry, this should be dou f1, this should be dou f1. Similarly, this will be f2 and dou xn, and we can go till dou fn dou fn dou x1 dot dou fn and dou xn. So this is we call Jacobian matrix. And we can find this value, maybe the constant value at some matrix. We can add xc u naught. If you substitute these values, we can come up some matrix. And similarly for the control, we can write dou f dou u dou f1 dou u1 dou f1 dou un, and this is dou fn dou u1, this would be dou fn dou un. This is we can call counterpart. Here we are not assuming the system is autonomous or not, just we are taking the general system f xu. Now we can do one thing. If we assume dou x dou u, this is delta actually, the small values, this goes to 0, the higher order terms go to 0 at a faster rate than the first order terms. Or we can write limit dou delta x and delta u, it's the known, we can write goes to 0, and we can write h dou x dou delta x and delta u, delta x we can assume to be 0, and similarly for the control part as well, h delta x delta u and delta u, limit delta x 0 delta u to 0. So this is also you can assume to be 0. So this is how we can ignore the higher order terms at the for the small part observation from the equilibrium point. And here, if you assume this condition, then this system can be considered as a linear system, this system. So how can write? So let me write one word. In a very small region of X and very small change in control input, the behavior of the part of system can be approximated by the locally linearized system, or we can linearized equations, or we can write delta x dot p. So here we can write, so here we can write this expression equal to this expression, sorry, this expression and this expression. And here this expression, here this expression is going to be 0 because at equilibrium point this function will satisfy. So here we can write delta x dot, we can write equal to dou x f xc u naught delta x plus dou u f xc u naught delta u. So this is, we can say, this is the equation number. Let us define. This equation is 3. Now we can say equation 3 is basically linear and time invariant equations. So this is how we can convert the nonlinear system. If you have a nonlinear system, and we can, if we apply this Taylor series expansion, we can get the LTI system. And this part already you have done multiple times. If you go back to our previous lectures, we have done. But why you are doing now? Because we need this part to study the Lyapunov first method. Now, let us take an example and we'll get the better picture of this part. So here, example. We can do one thing. We can take this example maybe later. Maybe we can directly connect how this concept is going to connect to the our Lyapunov first method. As we have discussed, that Lyapunov method actually valid for the autonomous system. So we can write Lyapunov first method only applies to the autonomous system. This is very, very important note, autonomous system. So we can write x dot equal to f of x. So here we are not going to consider the control in the system, only how we can, if the system is nonlinear, and how we can get the linear form. This is already have done. So for this case, we will not have this term. This Jacobian matrix will have only this part. And also u naught will not be there. So it is easy to get the linear system for this autonomous system. So now, for an autonomous system, we can write uh, for autonomous system, we can get the part of system delta x dot. We can easily write dou f xc and dou x delta x plus higher order terms, right? So this is basically, it is easier if you consider autonomous system. So we'll have this expression instead of this we'll have that expression, right? It is basically u naught will not be there. So the derivations will be more easier for the autonomous system. And similar to the previous, we can write here, we can write for, uh, we can write for small perturbations. For small region, we can write small region at xc. So we can write limit delta x goes to 0. This is the basically small perturbation from the equilibrium point, and we can write higher order terms xc delta x. We can consider it to be 0. So delta x equal to 0. We can assume it because the magnitude of this parameter h is very small at the region of the equilibrium point. Now, for this, if you consider this equation, let me define this, the equation number 4. The equation 4 can be written as, equation 4 can be written as delta x dot equal to dou f xc and dou x delta x. So this is basically linear system, and Lyapunov, based on the Lyapunov first method, we have 3 different conditions and how we can check the stability of the system. So first one is, if the linearized system, let me write in simplified form, we can write x dot equal to ax, for example. And here basically this part we are considering as a matrix. This is x and this is x dot. I'm just assuming. Okay. So we can write the system as x dot equal to x. Now, if the eigenvalues, of A are with negative real parts, we can say the equilibrium point xc is asymptotically stable. Asymptotically stable. This is very, very important. So this is the Lyapunov first method. This is the first point in the Lyapunov first method. And the second point, if the linearized system has one or more, it means the we can say you can use A. This is basically eigenvalues of A. More eigenvalues with positive real part, then we can say X is unstable. So these 2 points are very, very important in Lyapunov first method. So based on the roots of the or eigenvalues of the A matrix, we can comment how the system will behave at equilibrium point. So if it is the all the eigenvalues are negative real part, then we can, if it has negative real part, then we can say the equilibrium point is stable. And if it is one or more eigenvalues with positive real part, then we can say equilibrium point is unstable. And the third point, there is third point, which is if the linearized system has one or more eigenvalues with zero real parts and all remaining eigenvalues have negative real parts, the stability of Xc cannot be ascertained by studying the linearized system alone. Even we can write even stability in the small. So this is also important point. It is difficult to comment if it has um, remaining eigenvalues with negative real parts. So these three important points which talks about the Lyapunov first method. We'll have in the next lecture onwards how we can come up with the Lyapunov second method, and also we'll have the Lyapunov theorem. So I hope this part is clear. So basically we'll find the linear system, and from the linear system we'll see the eigenvalues. And based on the polarity of the eigenvalues, we can comment how the system stability would be. Let's stop it here. We'll continue from the next lecture.